Okay. Oh, whoops. I already got the five here. That's nice. Okay. We now get through 5.4 triple integrals. There are some ways in which this section will be very easy because we've already done double, and so we're just putting in one more variable. And then when we get there, there's one part that makes this material harder. I'll say what it is. It's just about visualization. So to start, well now, hold on one second. Hold on. I've given some version of this idea a few times now, but you want to keep on remembering, where ideas come from so that when you extend them, you don't lose track of things. So we'll do two recalls. One is one variable calculus. You take your domain and you split it up into a bunch of small intervals. Over any one of those intervals, you generate a rectangle and area gets built that way. We saw a form of 2D calculus, integral calculus, where we took a domain and we divided it up into rectangles. And then over any one of those are squares, honestly. Any of those, we generated a rectangular prism. And then using the volumes of these prisms, adding a bunch of those up, we came up with a form of volume. Let's go even further. We also saw polar was a different form of 2D calculus, 2D integral calculus, where again we had a domain, but we subdivided the domain in a different way. And we generated a slightly different form of quote unquote rectangular prism. Now it's a polar rectangular prism. And then we added up a bunch of those guys and came up with an idea for volume that worked well for different shapes than the first volume version. Okay, now we're going to three dimensions. So first things first, we integrate over a three-dimensional region, like a cube, for instance. Now, because we only visualize in three dimensions as humans, we've run out of dimensions to visualize a fourth dimension for the function. A popular or two popular alternatives are, I'll just write these two words, heat or density, as in, well, at some places it can be very in your cube, it can be very hot or very dense, maybe. But then as you move from that point elsewhere, you might have regions that are less dense and more regions that are more dense and regions that are very, very not dense, and then more dense regions. And so you can imagine that the density is described by a function of three variables. And you could theoretically integrate this function of three variables over this cubical region. So just keep in mind when we talk about integrating functions in 3D, we need an interpretation for the what would be the fourth dimension corresponding to the function values. And these words, heat and density, tend to be really useful for people. Okay, but before we even get there, we need to take our shape and break it up into pieces. And now the pieces are little cubes, so forth and so on. And we're going to take one little cube, like that one right there, and it's going to have three sides. I hope no one is surprised that the three sides will be delta x, delta y, and delta z, little changes in those three guys. And then the density will be roughly uniform in that little region. And so we'll multiply by the function evaluated at some x, I, y, j, z, k. And then collectively, this is going to give us our, um, I want to be careful writing what I'm about to write. I want to write, so I'll write it this way. The blue guy is delta V. That's how much volume there is. And then I'm just going to put in front of that F, X, I, Y, J, Z, K. Yeah. So we'll keep them separate from one another. Okay, what's going to happen? We are ultimately, so let's say that this region here has bounds in the X direction, A and B, in the Y direction, C and D, and in the Z direction, E and F. So we want to come up with a notion of a triple integral. Our total region is R. We're going to integrate over R this function F with respect to the volume. We will only be able to make sense of this if our Riemann sums have a nice limit. I equals 1 to n, j equals 1 to n, k equals 1 to n. What are we adding up? Well, the function values at f, x, I, y, j, z, k, delta x, delta y, delta z. And then this comes out to be, if this limit exists, the integral from a to b, the integral from c to d, the integral from e to f of the function, where we first integrate with respect to z, then y, and then x. And I'll just say or, and this is that Fubini's theorem again, but now we're in 3 dimensions. There are not only 2 orders of integration, there are now 6 orders of integration. I'm going to write just one more. We could do, for instance, E to F, C to D, A to B. And then on the inside, that's dx, and then dy, and then dz. Then there's, for instance, oops, dz, dx, dy, dx, dz, dy, dx, dz, dy, dz, dx. 6 different options. And they're all equal. All equal. If these functions are continuous, blah, 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 blah. In this class, we don't see examples of functions where they're not equal. Okay, let's just freeze there. That's just the background, the ideas to get us started. The examples are going to look just like the examples we saw for 2 variables, but with more work to them, obviously. So let's just get a few of these out of the way. This is just, it literally gives us the problem to evaluate. So this is 0 to 1, 2 to 4, 1, or -1, -1 to 5. They want us to integrate x plus y z squared, x plus y z squared, and the order is dx, dy, dz. dx, dy, dz. Okay, this is just calculations now. Just like with double integrals, first I do the innermost one. And this is with respect to x. Okay, there you go. That inner integral, oh no, sorry, that line was drawn wrong. It should be right here. The innermost integral integrates the x squared over 2 plus xy z squared. I gotta plug in a bunch of numbers now. That 5 is making me uncomfortable. 25 halves. Plus 5. Wait, hold on. Let me be smarter about this. If you plug in -1, you're gonna get 1 half. So you subtract that off, you get 24 halves. That's just 12. And then if you plug in 5, you get 5yz squared minus negative 1yz squared is plus 6yz squared. That was easier. dy dz. Okay, next up, we'll do the dy. 12y plus 3y squared z squared from 2 to 4 dz. Everything in blue here is the integral of the previous line. Plug in, okay, so 4 minus 2 is 2. So this is 24, 12 times 2. And then we get 16 minus 4 is 12 times 3 is 36. Let's just see, 12y, 4 minus 2 is 24. Yep, 3y squared. That makes sense, yeah. So we plug in 4 and 2 is 16 and 4 is 12. 12 times 3, looks good to me, okay. And then one more line. 0 to 1. No, not 0 to 1, sorry. 24z. We lose a factor of 3 here, plus 12z squared from 0 to 1. Looking 0 everywhere, you'll get nothing. So you're just going to get 24 plus 12 is 36. Voila. Okay, so that's a nice basic example. The main point or the takeaway of that one is just start on the inside and work your way out. And to make sure that when you're doing x, y and z are treated like constants. When you're doing y, x and z are treated like constants. When you're doing z, x and y are treated like constants. Okay, that's the first part. This guy, no, I'll skip that guy. And I'll skip that guy. Okie dokie do. Yeah. So now another recall. We don't just integrate over rectangles, right? In 2D, we had two types of regions that were really useful. Either you had a function of x and a different function of x, and the region was between there, or, whoops, you had two functions of y, and the region was the region between those two functions. So in the first case, it was g1 of x, g2 of x. The second case, it was h1 of y and h2 of y. And those were easy because we could use the functions g1, g2 of x, h1, h2 of y as the bounds on the inner integrals. How does that extend to 3 dimensions? I'm going to show you the first basic example, and then we're going to start building more. The first one is, imagine that you have some domain in x and y that you already know how to integrate over. So let's say, for instance, this one here. This looks like it could be thought of as a type 1 or a type 2. And then imagine that over that region, you had two functions of z. Here's the first function of z. There's the second function of z. Then you could set up, let's call this purple one, let's say it is type 1. So that's a g1 of x on the bottom half there. And on the top half over here, it's g2 of x. And y goes from a to b, let's just say. Then you would say, well, I'll take y from a to b, x from g1 of x to g2 of x. That gives me that purple region down there. And now, I'm not sure what letter, I'm going to use H here. Or, well, what are they using in the book? Okay, then whatever, they use U. U1 and U2. This is U1 of XY. And this one up here is U2 of XY. So we're gonna go like this: U1 of XY, U2 of XY, and then I throw the function in there. F of XY, whatever you're trying to integrate. So this is DZ on the inside, then DX, and on the outside of the, oh, I did this wrong, sorry. Oh, it's so embarrassing. If it's functions of X, then it's X from A to B, not Y from A to B. Sorry, guys. So then it's dy here. X. If it's functions of X from G1 of X to G2 of X, then we take X from A to B, not Y from A to B. That was stupid. Okay, so strictly speaking, this is what we're going to be working on here, is setting up integrals like this, where you first you do the X and Y variables in the way you would have done in 2D. And then inside of those, the innermost integral, you have to do bounds on Z. This can be a function of both X and Y. This is the part that I think is hard for people to understand. So let me just draw the region we actually just integrated over. It's it's kind of a cylindrical looking region, right? Between these two surfaces. If you saw this shape and you were asked to set up an integral over it, how would you do this? Right? It's one thing for us to show you these pictures and stuff, but it's another one to actually be able to do it. So here's one. Where is it? Come on. Yeah, let's do an exact example, and then hopefully it'll become clear. All right, bada boom, example. So they tell you in this one, integrate, they want you to do this. Integral over, it's a tetrahedron, so I'll call it T. This function, 5x minus 3y, with respect to the volume. And they tell you T is the tetrahedron. It's given by these equations. X equals 0, y equals 0, z equals 0. Those are the coordinate planes. And one more equation, x plus y plus z equals 1. Okay. Said set up or evaluate the integral of f over this region T. What does T look like? Every year I teach this class, every year that I teach this class, students will say, is there any way that I can do these problems without having to sketch? And the shortest and best answer to that question is no. No, you must sketch. It's every other way you would go about it is exceedingly difficult, pointlessly difficult, and unenlightening. So you've got to choose to practice sketching so you can reason about what these shapes look like. And then it should become quite easy setting up the integrals. So let's start and try to visualize what we're doing here. Well, there's this one plane, x equals 0. That's this guy right here. X has to be 0, but y and z can change. Okay. There's another plane, y equals 0. That's this guy here. Is, of course, let's try to use a different color. Z equals 0. And then there's this plane, this other plane, x plus y plus z equals 1. You can rewrite this as z equals 1 minus x minus y. So if z equals 1, in the zx plane, 1 minus x looks like this. One minus y looks like this. And then this is a plane, right? This expression is a plane here. So it's got to cut a straight line between these two. And now you can see the shape they're talking about. It's the region that's bounded by the four planes we have just drawn. That's one side of it. Back here is another side of it. Here is a side of it. And then there's this base side down here. Okay. We have visualized the region that we want to set up an integral over. Let's go back. How am I going to do this? How am I going to set this up? Well, the way I've been told to recall, the way we're trying to think about this is first we've got a region in 2 dimensions, a purple region maybe, that we know we can integrate over, that we could set up an integral over. Can you see the corresponding purple region here? I'm going to use this guy down here. How do I set up an integral over that region? Well, there's two ways that are both equally good. You can think of it as a type 1 region, where the first function right there is y equals 0. And the second one right there, I don't know if you can tell, but that's y equals 1 minus x. Right? That's what you get if you set z equal to 0 in our plane. And therefore, a double integral over that purple region can be achieved by going x from 0 to 1 and y from 0 to 1 minus x. So that's dy on the inside, dx on the outside. I've set up a standard double integral in Euclidean coordinates over that base there. And now I must, and this is kind of, tricky. Now what? I need two functions of x and y. Z has to be one function of x and y, representing the bottom of the shape. And then I need z equal to a different function of x and y to represent the top of the shape. What is the bottom of the shape? Hopefully it's clear. It is this same triangle. That's z equals 0. What is the top of the shape? The top of the shape is the thing we took so much time trying to figure out how to draw. It's that green plane there. What is that green plane? It's z equals 1 minus x minus y. Throw that bad boy in there. 1 minus x minus y. And so this is correct. And then what did they ask us to integrate? 5x minus 3y. Yeah, 5x minus 3. So that's dz on the inside and 5x minus 3y. Okay, so this is correct here. We can evaluate it. Why? But this is as far as the material goes that you are learning now. From here, it's just calculations. So what you want to spend time on, what you want to reflect on, what you want to get better at is what is on the screen so far. In particular, it is a hugely good use of your time to practice converting expressions, mathematical expressions, into shapes. And furthermore, to set up integral bounds that correctly describe those shapes. These integral bounds paired with dz, dy, dx here, collectively, the integrand doesn't matter. 5x minus 3y doesn't matter. But the rest correctly, accurately, cleanly, whatever, describes this tetrahedron. All right, let's race through some calculations. I get 5xz minus, no, let me not do it that way. Let's do it this way. 5x minus 3y. I'll just treat that all as one constant. Z evaluated from 0 to 1 minus x minus y. That's the innermost integral. Then I've got, I can't lose this guy or this guy. If I evaluate that, I get, whoops, 5x minus 3y, 1 minus x minus y, dy dx. I just plug in 1 minus x minus y for z. There's some expansions we've got to do here. 5x minus 5x squared minus 5xy minus 3y plus 3yx plus 3y squared dy dx. I don't know how much, yeah, well, are they all different? X squared, xy, y, yx, y squared, they are all different. Okay, so everything not involving y is 5x minus 5x squared. That picks up a factor of y. Everything involving one factor of y is 3x. Oh, those were two. Okay, minus 5x. All right, so that's minus 2x. Minus 6 minus 3 times y. So that becomes y squared over 2. And then I've got plus y cubed. This is from 0 to 1 minus x dx. And now here, I'm going to stop because it's a complicated polynomial, but it's one variable calculus, right? We grouped everything in x and y and integrated with respect to y. Once you plug in 1 minus x, this is just going to be a giant polynomial in x. That's one variable integral calculus, so I'm going to leave that to you guys. Okay. Still a bunch to get through because there's just so many little ways this can be tricky. Here's a good one. Find the volume of, yeah, this is what they tell you, the pyramid with base -1 to 1 cross -1 to 1 in the xy plane. And vertex 0, 0, 1. Find the volume of this pyramid. Yet again, the joy and the tragedy and the pain, the misery is to convert what is given as a description into a picture. Let's try and do this. Whoops. All right. What's the base? -1 to 1 in each direction. That's a big square. It's a 2 by 2 square. Okay, there's my base. -1 to 1, -1 to 1. And then they say the vertex is at the point 0, 0, 1. So in Z, it's 1 in the Z direction, like right there, maybe. If it's a pyramid, you can hopefully do the work from here. Can't see that one back there. Okay, for the sake of my drawing, let me draw that a little bit higher. I think it'll be clear if I put it there. Yeah, that's better. Boom. Okay, take your moment. How will you do this integral? I'm going to tell you right now, and you can maybe spend time trying to figure out why. We don't want this. So we do want to integrate the function 1, right? To find the volume, we just let the density be 1 everywhere and integrate. But if we set up this integral this way, well, the lower bound for z is clear. The lower bound would be 0. But the upper bound is the top of the pyramid. How will you express the top of that pyramid? It has 4 pieces. So you would have to break the domain into 4 pieces. 1, 2, 3, 4. And do a separate integral over each one of those for the different top pieces of the pyramid. We don't want to do that. Oh, well, okay. I can leave that on the screen, but hold on a second. Leave it on the screen, but just exit out. We don't want that. So the real insight you want to walk away with, if you can, is star. We can use any order we want. And some orders are better than others. So this is going to be a bit tricky. I would like to set it up so that x is the innermost integral. Let's set this as a goal. So we're experimenting, we're not intimidated, we're feeling creative. So we're going to need some kind of bounds. We don't know what they are yet, but I'm going to put x on the innermost, and then just to spoiler alert, I'm going to do dy dz. But let's just look at x, and we're going to integrate 1. We know we're going to integrate 1. That's not the hard part. If x is the innermost integral, can you conceive of the pyramid as being between 2 functions of y and z? Are there 2 functions of y and z, a lower function and an upper function, quote unquote, that describe this region? I'm going to try to give you a hint. If it's a function of y and z, then the domain is the y and z plane. This whole plane, y and z. Now, if you look at that plane, where does it cut the pyramid? Like if the pyramid was a piece of cake and the orange plane was a knife, where does it cut the pyramid? Try to draw that in. Oops. X is a function of y and z. Where are the negative values for x? Negative x values are over here. Positive x values are over here. So what is the lowest x values? Where is the surface where x is the lowest? It's back here. Oh, come on. It's this face of the pyramid. This is the low side in x. And then over here, this is the high side. This is the high side. X goes from the low side to the high side. Everybody see that? And that gives you your pyramid. This is preferable to the first order because the low side is a plane. That's easy. We're going to find an equation for that plane. And the high side is also a plane. We're going to find an equation for that plane. And we're going to be very pleased with the answers. Before we do that, we need the base, the y and z part, which we've got drawn in orange. How are we going to get that shape? It's where the knife cut the cake. I don't want to waste too much time on that one. You can do that by going from 0 to 1 in z. And from, if you think about y as a function of z, the lower one is -1 plus z. And the upper one, if y is a function of z, is 1 minus z. Let me just do that real quick on the side so I don't lose anybody. Here's the YZ plane here. Here's that triangle. Whoops. If Z is a function of Y, this guy is Z equals 1 minus Y. That's probably easier to see. And this one over here is Z equals -1 plus Y. Oh, no, I did that wrong. Sorry. 1 minus Y, and this one is Z equals 1 plus Y. So did I mess mine up? So if you solve for Y on this edge, you get Y equals 1 minus Z. And on this one here, you get Y equals Z minus 1. Oh, that's what I put, -1 plus Z. Okay, yeah. So the lower bound for Y is Z minus 1 or -1 plus Z. And then the upper bound is 1 minus Z. Boom, 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 boom. Now that we have accurately described the base, which is in the middle of the pyramid in this case, we need to describe the lower and upper planes. There's a number of ways you can work these out, techniques you guys have seen. You can maybe see these planes don't change in the y direction. They don't depend on y. So they can be expressed just as functions of z and x. And maybe it comes as no surprise that it looks kind of just like what we just did over here. I can use a -1 plus z, 1 minus z. Let me be clear now why that is. If you picture the pyramid, the base is somewhere like right here. We can't see it because this is z and this is x. So the YZ plane is right here. All we know is that the back end, the low end for x is over here, and the high end is over here. But now look, it's the same picture. Z equals 1 minus x, and z equals 1 plus x. Exact same idea twice. Okay, that's a lot of work, right? If you think about how much reasoning, how much thinking just went into even just setting up the bounds. We haven't done any calculus yet. We just set up the bounds. It's a lot of work, a lot of mental effort. Luckily, once you've done that, the problem is reduced to something that you already know how to do. Let's just do it real quick. Integral in x, one integrates to x. One minus z minus one plus z is negative 2z. One minus z minus negative one. Oh no, it's plus one. Okay. That's two. Minus z minus it's negative two. Okay, it's two minus two z. That makes more sense. Dy dz. That's supposed to be z, right? One minus z plus one minus z. Okay, now we integrate in y. We're gonna get that same thing again. We can do a trig, not trig, sorry, a u sub on this. I need to pull out a negative one half to get negative 2z. So I get negative one half, and then it's u squared, so it's u cubed over 3. That's 2 minus 2z. If you plug in 1, you'll get 0. So we just want to plug in 0, and we get 1/3. That doesn't seem right for me. No, 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 no. Is that right? 2 times 2 times, I'm just sorry, I'm just checking real quick in my head. The total area of the cube would have been 2 times 2 is 4 times 1, so it should have been 4/3, right? So where did I miss a factor of uh you plug in 1, you get 0, you plug in 0. Oh, cubed. Duh. Okay, good. Okay, so then that comes out to be 2, 4, 8 divided by 2 is 4. Yep, there we go. Okay, sweet. Let me see if I can get one more good one. Uh, yeah. Okay, let's do this one and we'll call it quits. They want us to integrate the triple integral e over of this function, sorry, root x squared plus y squared. That's our integral, or plus z squared, excuse me. Back to the volume. But e now, this is what it tells us. E is given by, it's between two things. The paraboloid y equals x squared plus z squared and y equals 4. Last one, bear with me. Summon your mental energies to get through one more of these. You must visualize. I want to put y here, x here. Z here. Take 2 seconds to decide what that shape looks like. It's a paraboloid, but it opens up in the Y direction. Bada boom, like so. There's our paraboloid. I'm so satisfied with that last line. And then Y equals 4 is probably right here. Yeah, that's Y equals 4 right there. So this is the top. That's the top. And this side here, let's do a different color on it. Do like the light blue one. It's my favorite color in here. Actually, it's my favorite color combo. This light blue with this magenta is great. Boom. This blue part here, that's the bottom. That's more or less all the hints you need to realize what we're about to try and do. But I'm going to ask you a challenge question. What is the base in this case? We've got y, the top and the bottom are y as a function of x and z. So we're going to have um, dy on the inside, and then outside maybe dx dz. So there's a base in the xz plane. What does it look like? It's a circle. And that circle has a radius of 2. And we could attempt to set up bounds in x and z to represent that base. And we are not going to do that. Any idea what we're going to do? What are we going to do? Polar coordinates. Polar coordinates in x and z. Okay, ready for this? Let's do x equals r cos theta. This is just for inspiration. Z equals r sine theta. We don't actually need to write that out. What am I going to do? Well, I'm going to take theta. I just scared the crap out of me. There's a fly on my laptop. You better run away. Okay, 0. Oh, no, he's go. Boom. More fly now. Okay. Oh, you gotta be kidding me. Saitama and One Punch Man. Okay. Believe he's gone. It's not clear to me if he is or not. Uh, Hold on. Okay. So we'll take theta from 0 to 2 pi. That's the obvious choice there. We'll take r from 0 to 2. The radius of that circle is 2. Hmm. What are the bounds for, so sorry, that's d theta. On the inside, I need dy now. The lower bound for y is x squared plus z squared. It's that paraboloid. The upper bound is 4. The integrand is root x squared plus z squared. And never, never, never forget to multiply by r if you switch into polar coordinates. Continuing, 0 to 2 pi, 0 to 2. I don't want x squared and z squared. I want to express it in R is R squared is x squared plus d squared. And this right here is R. So my whole integrand now is that dy dr d theta. Boom. And let's just get this guy done. First, I'm integrating in y. So I get r squared y from r squared to 4. Then what? This comes out to be 4r squared minus r to the 4th. Well, we're going to integrate that, so let's just do it. 4r cubed over 3 minus r to the 5th over 5 from 0 to 2. I'm going theta. Did I get that right? R squared. That's what I'm on. Make sure I get everything right. R squared y, so it's r squared times 4 minus r squared, so that's 4. R cubed over 3 minus r to the 5th over 5. I believe that. Then I plug in 0, I get nothing. So we plug in 2, we get 2, 4, 8. 32, 32 over 3. Minus r to the 5th over 5. R to the 5th is also 32. And then this is all integrated 0 to 2 pi d theta. Well, that's all just a constant. So this is going to be 2 pi times 32 times 1/3 minus 1/5, which is 2/15. 2/15. 2, 4, 64, 120, 128 pi over 15. 5 minus 3 is 2 over 15. 2 times 2 is 4. So, yeah, I believe it. Boom. Okay, sweet. I covered everything, all the sections that I wanted to cover. So the homework should be complete now. There will be another quiz on Monday. And please keep your eyes open for this project that I'm going to post this weekend, especially if you want to make up for anything that you've lost, if you missed a quiz or you missed the homework, or even if you're done, you just want to do extra credit. But more information on that to follow. And as always, please email me if you have any questions. Good luck with everything. Have fun. Talk to you guys later.